Boom. Hello and welcome back to Calculus 1, section 5.3, Fundamental Theorem of Calculus. So this theorem, the title is so grand, right? What the theorem does is it connects derivatives and integrals and shows that derivatives and integrals are opposite of each other, opposite operators. We know already from the section of antiderivatives that, in quotes, integrals will undo derivatives. And we also know that when we perform integration, and we have plus c, you can take the derivative to check if you did your integral correctly. So now we are going to mathematically put those two together. This is a purely theoretical section. We don't have any calculations here to do. It is a pure concept, and if something like this is showing up on the exam, it would generally be either writing a paragraph or writing the formulas and explaining things. There are no calculations where you get 7 at the end and stuff like that. So fundamental theorem of calculus has two parts to it. The first part is the part on calculating the definite integral, which is what we saw last class instead of that very lengthy Riemann sum calculation. So part one of the theorem is to call it definite integral. Is the integral from a to b of f of x dx is equal to the antiderivative capital F of x from a to b, which is f of b minus f of a, which is the calculation we performed last time. Now, all of the problems that we did so far, so integral 3 to 6 of x plus 9, I don't want to do 9, I'm going to do 1, because I don't want to compute this forever. So all of the integrals of this type, you can have whatever function in there that can be integrated, so you can end up with the sine x, you can end up with the e to the x, you can end up with whatever else you can do. We are going to score x squared over 2 plus x as the antiderivative, and you would compute that 3 to 6. So we are getting 36 divided by 2 is 18, plus 6 minus 9 halves, and then minus 3. Right, while we compute this. So 18 plus 3 is 21, minus 9 halves, and then we have 42 minus 9 is 33 over 2. What happened?
No. No.
All right.
I forgot about the negative 3 thing.
Oh, okay. Another one of these would be that the integral 0 to 2 pi of sine x dx is equal to 0, which is what we calculated last time. Fundamental theorem of calculus is the definite integral. We are not talking about the area. We are talking about the value of the integral, so you will not jump through the hoops to find the parts of the function that are negative and figure out the absolute value, right, area, and so on. The definite integral computes the value of the integral as is when you plug the limits, and that's the end of the story. So the definite integral is computing this. Now, if the question asks calculate area under the curve, you have to worry about. So this question here computes the value, so not area. Now, this is a net area, right, which is 0. You have 2 minus 2 is 0. But this is not an area that you can color, which is actually 4. and we've seen that problem last time, so go and review that problem if you have no clue what I'm talking about. So that's part one of the fundamental theorem of calculus, and part two, which is what is new stuff for you now, is to write that the derivative of the integral of f of t dt, where this goes from a to x, is equal to f of x. So this is the one that we are learning now. And you can clearly see both integral and differential operators present in this formula. And you kind of see that you have over here this f of t and you have f of x, and it's the lowercase f. That means that if I'm to plug here cosine t, I would get here cosine x, because it's the same lowercase f. All right? So whatever is in the formula as a variable t, it's going to be in the answer with a variable x. It doesn't matter what you put. All right? Here, a heart of t is going to give you the heart of x back. There you go. That's the function. Right? So now, what are we... again, this is theoretical now. We are going to first show the short proof and derivation for this. We know that when we integrate function, we get the antiderivative, and its antiderivative will be computed between a and x. And I still have to apply derivative to it. So now I have the derivative applied to what we have as f of x. You plug in the upper limit first, minus f of a, which you plug in the lower limit. Now that a is a number of some kind, so we see that this part over here ends up being constant, right? So now when you apply the derivative, you have d dx of f of x, and then you have minus 0, because the derivative of a constant is 0. So now if the integral of lowercase f is a capital F, then the derivative of capital F is the lowercase f, and here's your f of x. So this is the quick proof. It's just a calculation of the definite integral, nothing special. We don't know what the function is, so we write it as in general terms as the antiderivative. Capital F, compute from a to x, so it's f of x upper limit minus the lower limit, so f of x minus f of a. F of a is constant, that goes to 0 in the derivative, and the derivative of capital F is a lowercase f. So we got to the point where we see this formula, and we see that the derivatives undo integrals. Therefore, in your later work in calculus and differential equations, when you are taking the derivative of the integral or integral of the derivative, you just get to cancel them out. Just like you would cancel inverse sine and sine, right? And keep the argument, or e and ln x, right? Now, that's happening on the function level. So that's a function composition and inverses. It's not the same, but it appears to be the same. So I would say it functions the same way, even though here we're talking about operators. In other examples that I mentioned, we're talking about functions. So if you are to see a problem for this, you would see it as d dx integral, let's say 5 to x of e to the sine t dt. You can't integrate this, but you immediately know that the answer is e to the sine x. And that's it, right? It has to be the same function, right, that you started with, except the variable is is x. It's no longer t. So it doesn't really matter what you get here. You will get the same on the other end, just in terms of x. And the main idea is that actually this happens. That's what happens. The derivative cancels the integral. You are going to see this immediately in Calc2, and you are going to see it again in differential equations should you push forward with math. So there are going to be instances when you are going to actually use this down the line. And now I would like to ask if anyone would tell me, why are these two operators completely opposite of each other and able to cancel each other, outdo each other? Why is that happening? Why is the integral opposite, right? Why is the antiderivative? Can you go back to either definitions or whatever and tell me why they're opposite? Can anyone tell me the definition, the limit definition of the derivative at this point? We did that like 16 years ago. What was f prime in terms of the limit? Limit h, very good.
X plus, sorry, f of x plus h.
Yes.
Minus f of x.
Very good. Over h. Nice. Does anyone remember the Riemann sum for the integral? It starts with the limit where n goes to infinity. It was last week. Summation from 1 or 0, doesn't matter, to n of f of ci times delta x. Very good. So do you see it? Do you see it, how they're opposite, how they're completely opposite?
The x plus h is delta x.
No. That's not where I'm aiming. Actually, you picked the one thing that I would not go for. Like out of everything, it's the one thing you found one thing that can arguably mess up my argument completely. Completely opposite. That's the key word. Completely opposite. Actually, no. That plus h works. Wow. All right. Can you find more? Nice. Division, multiplication. Can you find one more? Nice. See, when you start thinking about these things, they just pop out. These guys are completely opposite, and this is x plus h, and dx is b minus a, right? So these guys are completely opposite of each other. Completely opposite of each other because the opposite operations show up 100%. This is addition. This is accumulation of all things. And this is difference. It's a slope, right? You have h goes to 0, n goes to infinity. You have also, say, everything is backwards. And they undo each other, right? You know that if you want to solve x plus 2, you subtract 2 on both sides. If you want to do 3x equal to something, you divide by 3 both sides. So they completely undo each other in this. So that's it. I have nothing else to say other than be careful with the definite integral. Make sure that if they ask for the area, you are looking for area. If they are asking for the value of the definite integral, it's the value of the definite integral. You don't have to break it apart and look for little parts that go below x-axis and so on. Yes?
So for the definition, then the negative number makes sense, right? With the,
Yes, yes, yes. Because you have the concepts of negative energy, right? Yeah, you have the concepts of negative energy. You can have, so sure, I will argue that the area needs to be positive. Area needs to be positive because you are coloring, right? And you have to have positive area to color. Now, this is all done in respect to the x-axis. So, you know, area in application, right, around us, the x-axis is not imposed. It is our thing that we impose on a problem so that we can work on functions and have, right, reference points and so on. So because of that, right, because of that, we have the issues with plus and minus and negative and so on. But, you know, if I want to color this, it just has area and that's it. Now, if I put the x-axis here, that's my problem. All right, that's my problem, that's my issue. And then I have to deal with the negative area. Because this is still going to, no matter where I put that x-axis or which way I put the x-axis, I have to deal with the issues and problems I created. But without x-axis, I can't do computation. So, right, there's no free lunch. Yes?
So a different integral, is it equal to the area or the net area?
Net area.
So the integral of sine x, if it's equal to the net area, is 0.
Yes.
So I remember last time we said it's 4.
Yes, we did, because that's the area, area that you color. So area that you color is not the net area, right? The net area is going to be the area that you compute through the definite integral, and then if you have to deal with. So your lab will address, there is a problem on your lab, or 2 or 3 problems on your lab. They give you the graph on the lab, and you are supposed to calculate the area of the shaded region, and I believe there are some areas that dip below x-axis. So you will be practicing that there, and obviously the homework will also have those concepts. So yeah. All right, well, restart the stream for the next section, which is also very short.